Hello there, physics students, and welcome to this video, our second video on light. And we've got some really cool stuff for you for this video, okay? We're going to talk about diffraction and color mixing here. All right, so diffraction. Diffraction is a word that we attach to this strange phenomenon with light, okay? And really with all waves. So if I have a light source here, and then it goes through this, I don't know, maybe it's a window, okay? So the shadow, what's the shadow of this going to look like? Well, the shadow is going to project, it's going to make a larger projection, right? It's going to project the light onto, oh, I don't know, maybe there's a wall behind here, okay? So what happens though is that we don't get a sharp edge of light like we would expect, okay? We would expect that light would be cut off directly, okay? But that's not what happens. What actually happens is that we get a fuzzy line right here. We get a very fuzzy line throughout this, okay? So how can we explain this phenomenon? Well, if we take a look at a single wavefront, okay, what seems to happen is that as this wavefront hits the barrier, part of the wavefront will be blocked, okay, and then as this barrier goes to the other side of the barrier, alongside of it, it seems to get, it seems to turn and spread out just that little bit, okay? So they call this the tendency for a wave to bend around the edge of a barrier is called diffraction. Okay, so that's what diffraction is. It's the tendency for a wave to bend around the edge of a barrier. But how do we explain this? Well, there's a guy named Huygens that had a brilliant idea on how to explain this, and that's what we're going to share with you now. So this is Huygens' principle. Every point of an advancing wavefront is a new center of disturbance from which emanate independent waves in all directions. Okay, let's parse this. Let's break this down. Okay, so each point, every point in an advancing wavefront. Okay, so here on the side here, I have an advancing wavefront. Okay, so this is time t1, t2, t3, and now at time t4, the wavefront is here. Now we would expect at time t5 that the wavefront will be, there'll be one more wavefront in this array of waves. So we'd expect to get one more wavefront right here. Now, according to Huygens' principle, we can figure out where this wavefront is. I know this sounds silly, okay, but trust me here for just a few minutes, okay? According to Huygens' principle, it says that every point on an advancing wavefront is a new center of disturbance. So every point on an advancing wavefront is a new center of disturbance. So any point, I just picked some random points on here, is a new center of disturbance. Okay, so that means that wave fronts will radiate out from each center of disturbance. Okay, that's what happens. What's a center of disturbance? Well, think of dropping a rock in a pond, and then you will, what will emanate from this rock will be a series of circles, right? Okay, and this series of circles, these would be the wave fronts that are advancing, okay? So this is a center of disturbance, okay? So each one, any point on this line can be thought of as a new center of disturbance, okay? So after some time, another time interval then, we'll have all of these wave fronts will be emanating from these individual points. Okay? So where is the new wavefront? Well, if we draw lines that are tangent to these circles, then we'll get our new wavefront, and our new wavefront will be right here, okay? That's Huygens' principle. Every point of an advancing wavefront is a new center of disturbance from which emanate independent waves in all directions. Okay. Can you see how this is going to help us with our barrier problem and to explain this? How this model, okay, and boy, we've been after good models this entire year. A lot of our models have been mathematical. This is not a mathematical model. This is a stated principle. Okay, so not all models are equations. Some models are just stated principles. So if we apply Huygens' principle to wavefronts approaching a barrier, okay, and this is what we have here. We have a barrier. Oh, didn't mean to do that. There we go. So we have a barrier here. Right? So if we apply Huygens' principle here, then as this wave front approaches and passes here, okay, each point on this wavefront can be thought of as the center of its own disturbance, okay, independent. So we can draw fresh wavefronts emanating from each one of these mini disturbances. Okay? And we can see what the new wavefront will look like. Okay, that last one's terrible. There we go. So if we draw tangent lines in front of these, and then we can do this, we can apply Huygens' principle again, okay? And again, and again, and again. And you can see what will happen to these disturbances, okay? We'll get this light ray bending around the edge of a barrier, okay? Hey, that's Huygens' principle. So using Huygens' principle, we can predict what will happen when a light wave passes through a very narrow slit. So when it gets to this point, each point on this wave is going to act like its own point source. And it's going to keep doing that. So eventually, we're going to get a wave that does this. Okay, we'll have this kind of diffraction pattern. All right, so now I'd like to talk about mixing colors of light. Okay, now I'm talking about the primary colors of light, not the primary colors of paint or pigments. Okay, so that's something you learned that's different than what you learned in art. Okay, because we're talking about mixing light. So if I were to take a red spotlight, okay, and I were to shine on top of that a green spotlight. So I'm going to take this green spotlight and shine it right on top of the red. And then I'm going to take the blue spotlight and shine it on top of both of these. So what am I going to end up with? What color do I get when I mix red, green, and blue light? Okay, when I mix red, green, and blue light, I get white light. Okay, that's why we call them the three primary colors of light. Okay. This is also called the RGB color space, and it's what your computer monitors do to create the different colors that you see on your computer monitors. Okay, there's a red dot, a green dot, and a blue dot, and each one is the intensity of each is controlled. And if you control it in just the right way, you can produce any other color using just red, green, and blue light. So in this example right here, this is my red, green, and blue. Okay, I'm controlling red, green, and blue. I can start at 0. I can go all the way up to 255. So for each one. So if I have 0, 0, 0, that's an absence of light. An absence of light, that's what we call black. okay, and that's what you see there. Okay, now if I change the red to 255, we'll get pure red. Okay, if I change the green to 255, we'll get a pure green. Okay, and then of course, if I change the blue to 255, we'll get a pure blue. All right, but what do we get if I mix, say, red and blue? Red and blue, what do you think that makes? You're probably right. Red and blue make magenta. Okay, so red light mixed with blue light gives you magenta light. Okay, and what if they're all three 255? What did we say it was? We said it would be white, and that's what you're seeing there. 255, 255, 255. That's pure red, pure green, pure blue, all mixed together. That gives you white. Okay, what if we take the blue out? What does red and green make? Okay, red and green make yellow. Okay, and let's see, what two haven't we mixed together here? We have not mixed green and blue together. Green and blue mixed together give us this blue-green that we call cyan, C-Y-A-N. Here, let's write that out. So I thought this chart might help you remember. Of course, so if we mix red with red, of course we get red, okay? If I mix red with green, then we get yellow. Okay, if I mix red with blue, then we get magenta or purple. So magenta. Okay, green with red, let's see, green and red, that's yellow again. Green with green is green. And then green and blue gives you cyan. Okay, cyan is a blue-green. Okay, and cyan is about that shade, so we'll put a C there for cyan. Okay, and then of course red and blue, that makes magenta again. Blue and yellow, that makes cyan again. And then blue and blue, of course, makes blue. Like so. Okay, now when we're talking about colors, we call cyan the complement of red. Okay, why would we do that? Okay, what colors does cyan contain? Well, cyan contains the green and the blue. Okay, so I've got the green and the blue right here. And if I mix it with the red, then I've got red, green, and blue, because then they all make together, we call them the complement because they make white. All right. So each primary color has a secondary color that is a complement. Okay, and so we call magenta, yellow, and cyan, we call those the secondary colors of light. And we call magenta the complement of green, and we call blank the complement of blank. I'll let you fill that in. Okay, well, this has been an introduction to color. In the next video, we'll start talking about pigments and what happens when you mix pigments, okay? Because pigments are themselves a subtractive process, okay? So if you see red, okay, if you're seeing an object that is red, then we know that white light goes in, okay? So we've got red, green, and blue going in, but only red coming out to go into your eye. So that must mean that green and blue are being absorbed, okay? So that's what we call pigments, a subtractive process, because each substance, each pigment is going to absorb some primary colors and reflect others, okay? Hey, more about that in our next video. All right, hey, thanks for watching. We'll see you in the next video.